Hi, everybody, and welcome to another Fluid Earth Dynamics. This one is on basic wave mechanics, and we're just going to look at some very basic properties of water waves that we'll be using in class. So first of all, hopefully this is a review, because hopefully you saw all this in high school. We're going to talk about just the basic geometrical properties of waves. And I should say that for our purposes, everything that we're going to talk about falls under the category of what we call linear surface gravity waves. So surface gravity waves are, it's just a complicated name for the things that you see on the surface of Lake Harriet or even on a puddle when the wind blows. If you drop a rock in the water and make waves, they're surface gravity waves. They're surface waves because they're on the water surface at the air interface, and that's to distinguish them from internal waves that are actually inside the water. They're kind of mysterious, but we don't have time to talk about those. They're gravity waves because gravity is the restoring force that's trying to make the water surface flat. And they're linear because they are not so tall that complicated nonlinear effects come into the math. So the math is relatively simple. Okay, so a reminder of some basic geometrical properties to start with. We have the wavelength, which is defined as the horizontal distance from any two corresponding parts of the wave in successive waves. So usually the drawing is crest to crest, but the wavelength can be defined as any part to its corresponding part in the next wave. We're going to be talking about crests, and we're going to be talking about troughs. So those are obviously the top and bottom of a given wave. The wave has an amplitude A, and the wave height, which is probably the thing that's more intuitively familiar, would just be twice the amplitude. But for many purposes, it's actually easier to talk in terms of the half height, which is the amplitude. You can think of the amplitude as the deviation of the surface away from its average position as well. And then finally, there's a thing called the phase velocity, and that's just the speed that the actual waveforms are moving through the water. And I probably will just refer to this as the wave speed for the rest of this talk, but the reason it's called the phase velocity is to distinguish it from something called the group velocity, which we're not going to be working with, but represents a slightly more subtle definition of how of the rate at which energy flows across the surface through the waves. So this is the one we're going to be using, though, just this phase velocity, and that really is just as simple as the speed at which the geometric forms move over the surface. So, as I said, these are surface gravity waves. These are the common waves that we see all around us on lakes and oceans. And something that I'm sure you've heard before, but I want to reemphasize, is that the waves move energy from place to place, but they don't move water. So the water stays put. It does move locally while the wave is passing through, but on average the water stays put. But energy moves from place to place. So, for example, when a big typhoon or a hurricane stirs up the water surface someplace in the middle of the ocean, that energy is radiated out from the location of the storm via the surface gravity waves, and it may end up impinging on the shore in places that are very, very far away. For example, many years ago it was determined that most of the wave energy coming ashore in Southern California was coming from typhoons in the Western Pacific. So the energy flows across the ocean at global scales, but the water, for the most part, when a wave passes through, stays in place. Okay, well, so there's some basic relations that apply to all waves. The most basic of these is that the wave height is just twice the amplitude, which I already mentioned. And then the other one is that the phase velocity has to equal the wavelength divided by the period. And that's just because of the way these three things are defined. So for I think the easiest way to think about this is just that if you move a distance lambda and and a speed c, the time that has to take between the distance that you went and the speed that you went is given by exactly this little bit of algebra. So it's just the basic relation between distance, time, and speed. Okay, well, you will be very disappointed to know that we don't have time to develop the so-called dispersion relation in this class. But a long time ago, Airy, whose name I haven't mentioned before now, but who was one of the great 19th century physicist, a British physicist, this is the same Airy that came up with Airy isostasy, developed the basic physics of surface gravity waves, a linear theory in which he was able to drop some of the more complicated effects. And again, this is something that we don't have time to actually derive in class, but the upshot of Airy's work was that there's a relation between the frequency of the wave, which is given by this quantity omega over here, and the wavelength and the water depth that's given by this equation here. So the frequency is just another way of expressing the period, and actually let me write this down because I don't think that's in any of the slides. So the frequency is defined as omega equals 2 pi over the period. And we're also going to need this wave number k. So k is equal by definition again to 2 pi over the wavelength lambda. And so k is to wavelength what omega is to period. So wave number and frequency, which are basically just two alternative versions, for the period and the wavelength. So Airy came up with this relation that connects the frequency, omega, actually let me switch back to my laser, to k, the wave number, g, the acceleration of gravity, k again, and then h, the water depth. So apart from gravity, we have just basically period, wavelength, and water depth as part of this. And then there's this, and probably when you learned about hyperbolic tangents somewhere back in the distant past, you thought that it was just some weird mathematical abstraction that you'd never see again. But here it is. It shows up in our basic equation that connects frequency, wavelength, and water depth for surface gravity waves. So this equation applies for all surface gravity waves, regardless of the water depth, regardless of the wavelength, etc. If you rearrange this using the fact that the phase velocity is related to the wavelength and the period as we described, in fact, you should be able to convince yourself that Cp, the phase velocity, is equal to omega over k. That's just from the definition that we gave in the previous slide. Then you can rearrange this equation into this one, which is just a little bit more useful for us because it relates the speed of the waves, their phase velocity, to their wavelength via k. And the period actually drops out because if you know any two of the quantities in this equation, you know the third one. So the phase velocity just depends in this equation on the wavelength via k, the acceleration of gravity, which is going to be constant for our purposes, and then the water depth. And once again, the terrifying hyperbolic tangent is there. So just a little refresher, the hyperbolic tangent is defined this way. It's actually just a composite function, sums and differences of exponentials. And it has this interesting shape here that you see. It kind of flattens out as its argument becomes large and becomes constant, and then it goes through zero just like this. So it makes a kind of a nice looking S-curve. That's the hyperbolic tangent. Now, the equation that I just gave, the so-called dispersion equation, is called that because it relates the speed at which the waves move to their wavelength. We're actually not going to use the full dispersion very much, but it has two interesting and very simple limits that are actually quite useful. The first limit is the one where kh, the product kh, goes to infinity. And if we go back, I'm just going to go back a couple to this, you notice that the argument to the hyperbolic tangent here is this kh function, or kh product. So as kh becomes very large, then that's called that's the so-called deep water limit of the wave. And let's just take a second to look at what geometrically it means when kh becomes large. It means that either h is large or k is small in some relative sense. So a small wave number means that you've packed a lot of waves. I'm sorry, I just messed that up. We'll start this again. So this deep water limit is when KH tends to infinity, so it becomes large. So that means either the depth is large or the wave number is large. So a large depth is pretty obvious, the water is deep. A large wave number, because the wave number, remember, is 2 pi over lambda, means that you have packed a large number of waves into a short distance. In other words, the wavelength is small. So the waves are short in terms of wavelength relative to the water depth. So that's the so-called deep water limit, and that would be the case where KH becomes large. In the shallow water limit, we're talking about KH getting close to 0. Now remember, KH is always positive because these are real physical waves that we're talking about, so they can't have things like negative wavelengths and negative depth. So for a positive KH that's close to 0, that means that either the depth is very small or K is very small. And remember, because K is inverse to wavelength, if K is small, that means a large wavelength. So the picture I want you to have for shallow water waves is that the waves are long relative to the water depth. And the picture I want you to have for deep water waves is that the waves are short relative to the water depth. And you notice that in neither one of these does the wave's amplitude appear. So the wave amplitude is not part of this picture. Deep water and shallow water are relative terms for waves, and they refer only to the relation between the wavelength of the waves and the water depth. Shallow water waves are long compared to the water depth. Deep water waves are short compared to the water depth. It has nothing to do with the absolute value of the water depth. So you can go in your bathtub and make some deep water waves by splashing with your hand, and they'll be deep water waves as long as their wavelength is short compared to the depth of water in the tub. And believe it or not, you can make shallow water waves in our Earth's ocean, which we think of as quite deep, if their wavelength is long compared to the water depth. And when we do our in-class work, we're going to see some examples of those. But to give the game away a little bit, tsunamis, which are the common, unfortunately all too common, waves that are generated in the ocean from earthquakes are deep water waves. Are shallow water waves, even though they're in the ocean, which we think of as quite deep. And the reason they're shallow water waves is that they have wavelengths of hundreds of kilometers, and the ocean has a depth of only a few kilometers. So, okay. So the two limits are useful because in those two limits, the hyperbolic tangent function behaves in an extremely simple way. When its argument becomes large, the hyperbolic tangent tends to a constant value of 1. And when its argument becomes small, and the argument is just the x that you're putting into the function, when the argument is small, the hyperbolic tangent behaves in that limit, so very close to 0, as if it were just x itself. So the hyperbolic tangent becomes basically like x. So hyperbolic tan of x becomes x. So putting those two limits into our basic area equation for the dispersion of the waves, and in particular putting it into the form that involves the phase velocity, we see two really simple relations for the phase velocity that emerge. When KH is large and the hyperbolic tangent tends to 1, the phase velocity Cp becomes just equal to the square root of g over k. So it now depends in a very simple way on the wavelength. And in particular, because it's 1 over k, if we have a high wave number, which means short waves, small wavelength, then we have a small phase velocity, and vice versa. So what this means altogether is that for deep water waves, the speed depends, first of all, it depends only on the wavelength via k, as you can see this. The depth is now gone. And it depends on k in such a way that it's inverse to k, it's actually the inverse square root, which means that it increases as the wavelength increases. So the basic takeaway message from this is that for deep water waves, longer waves move faster than short waves do. This, again, has nothing to do with how tall the waves are, has nothing to do with their amplitude. This is all about the wavelength. But long wavelength waves move faster than short wavelength waves. And that's why when you have a hurricane or some other storm that generates waves of all different wavelengths, because it's kind of messy and chaotic and it excites the sea surface at a whole range of wavelengths, the long wavelengths tend to pull away and move faster than the short wavelengths, and they are the ones that reach distant places first, and we know those as ocean swell, actually. In the shallow water limit, when KH is becoming small, remember it's not this means tends towards 0, not equal to 0. So when it's small, if you go back to the basic dispersion equation and substitute kh tending to 0, in that case the argument to the hyperbolic tangent becomes equal to the value of the argument itself, and then the limiting value for the phase speed, Cp, the speed at which the waves move, is just that they move at a quantity given by the square root of g times h. So g, the acceleration of gravity, again, h, the water depth. You notice now the wavelength no longer plays a role. So the waves now move at a speed that's controlled only by the water depth. In particular, the deeper the water, the faster the waves move, and vice versa. So we say that waves in shallow water are non-dispersive because all the wavelengths move at the same speed, and that's set just by the water depth. So the next couple of slides just show the algebra of this a little bit more. In the deep water limit, the kh, which is where kh tends to infinity, this tends to 1, and our wave speed goes to this g over k value, which is just written out here in terms of the wavelength. And then, sorry, I made a mistake. Oh, no, this is right. So this is just reiterating the deep water limit. This is now a relation involving omega, the frequency, which is just the product of k and the phase speed, and that's equal to the square root of gk value. If you work the algebra a little bit, you can derive this equation. I'm going to leave that to you guys to do on your own. But this one is just an algebraic rearrangement of this one. And it has a useful property, which is that if you put in the value for Earth's gravity and work that through with 2 pi, this is about 10, this is about 6, you end up with a very simple relation between the wavelength and the period for deep water waves. So this is a useful limit to know about. This just says that if you take the period, t, and if you're at the beach, you can easily measure the period just by counting the time between successive wave crests. You square that, multiply it by 1.5, and you get the wavelength of the wave. So, for example, for a typical deep ocean swell wave that you might see at an ocean beach, which might have a period of, say, 10 seconds, if we take that and square it, we get 100, and we multiply that by 1.5, we have 150, so they have wavelengths of 150 meters. So 150 meters is a pretty respectable wavelength, more than a football field long for those big 10-second waves, but of course it's still short compared to the depth of the ocean. So they, in an open ocean, those long period waves are still deep water waves. Okay, so the last topic that I want to talk about under waves is just the motion of the water. Now, I said that on average the water doesn't move. The waves move energy across the ocean, but they don't move water across the ocean. That doesn't mean that the water particles are standing still the whole time. The water particles do actually move as the wave comes through. They make motions that for a deep water wave are circular in nature. So they go up as the wave crest is coming in, and then they go down again as the wave transitions from crest to trough. And on average, the water particles describe a little circle. So that circle has a diameter that's equal to the wave height, so it has a radius that's equal to the wave amplitude. And the time it takes the water to go around the circle is the wave period t. So you can easily work out from that, and I leave this to you to do, and we'll work with this a little bit in class, the speed that the water particles must be moving as they execute this motion. In shallow water waves, when the waves are interacting strongly with the bottom, the motion gets a little bit more complicated, but not much. Instead of making circles, the water particles make oval patterns that you see here. So they move in an oval path because the waves are now kind of, if you like, you can think about it that they're being squashed. The water particle paths are being squashed by interaction with the bottom. And then right at the bottom, which is where waves move sediment, so that's of interest to us as earth scientists, the water particles just move back and forth. So this would be the pattern of motion in these waves. Oops, and actually there's one thing I meant to mention, and that is for the deep water case, the circular motion dies off exponentially with depth into the water column. So the circular motion has the properties that I described at the surface, but it gets weaker and weaker as you go down into the water column. And the noteworthy thing about this is that the rate at which the water motion decays is controlled by the wavelength. It's actually an exponential. So it decays pretty quickly, and it decays faster for short wavelength waves than long wavelength waves. Okay. So then the last topic, which we're just going to start on here and then we'll develop more in class exercises, is just the idea that waves, as they transition from deep water to shallow water and eventually come up onto the beach and break, can move sediment. And they do this by getting the sediment particles going, and then as the particles are agitated, if there's any net flow of water associated with the waves coming into shore, that will cause a net motion of sediment. And you're probably thinking that this is a direct contradiction to what I just told you, which is that the waves don't move any water, and they don't move water until they get very close to shore. And in particular, when waves start to break, they can move quite a bit of water. And you may have experienced this if you've ever been swimming and felt an undertow or felt the flow of water associated with waves dragging you along the shore or anything like that. That's called longshore currents. And so, interestingly enough, as waves come into shore, as shown here, if they come in at any angle to the shoreline, so in this diagram they're making an angle that you see here between the wave crests and the average direction of the shoreline. If that angle is anything other than 90 degrees, then there will be a component of motion of the wave-induced motion that's parallel to shoreline. So if we take the vector of motion of the incoming waves, which is VW in this sketch, and we resolve it into a component perpendicular to shoreline and parallel to shoreline, then the component parallel to shoreline is the component of motion that ultimately sets up this so-called longshore current. That's the flow of water along the shoreline. If you have a longshore current and the waves are agitating and moving the sediment as they pass overhead, then that longshore current will transport some of the sediment in its direction, and that's called the longshore drift. And in class, we will develop this idea further. We're going to make some sketches and do some work with how longshore drift erodes and deposits sediment on shorelines that will help you make informed decisions on buying beachfront property when you get rich. But for now, I just want you to think about the notion that the stronger this longshore current, the stronger the wave-induced sediment transport is, so the higher the sediment flux. And think about the relation between the strength of this current and this angle between the incoming, the direction of the incoming waves and the average direction of the coastline. And that's all for this, and we'll develop these ideas further in class. Bye-bye.